In this video, I'm going to go over the Chem 118B ATC worksheet 9. And this worksheet is going to be about conjugated dienes. So let's get started on the predict the thermodynamic and kinetic products for the following questions. So we have here a conjugated system with DCl. So to determine the kinetic or thermodynamic product, the first thing I do is I try to form my most stable carbocation as in the first step. So I see that I can form a tertiary carbocation at this carbon. If I grab the deuterium ion here and kick off the chlorine group, which will give me this tertiary allylic carbocation where it is conjugated or next to this alkene over here. And since this is our most stable carbocation, when the chlorine attacks that carbocation, this will give us our kinetic product. Our thermodynamic product will be when the double bond is in our most stable position, which we see here. Our thermodynamic product is a tetra-substituted alkene, whereas our kinetic product is a di-substituted alkene. So when we form our tertiary allylic carbocation in the first step, we could do resonance to form our most stable double bond, our tetra-substituted alkene here, but our tertiary allylic carbocation gets converted into a primary allylic carbocation, which is less stable, and which is why it requires more time to achieve this product. So thermodynamic product is more stable in terms of the alkene, and kinetic product is more stable in terms of the carbocation intermediate. So let's move on to the next problem here. The first step is to form the most stable carbocation, which we see is this tertiary allylic carbocation here. When we do the resonance, we see that we convert that tertiary allylic carbocation to the primary allylic carbocation, but we also converted it from a mono-substituted alkene to a tri-substituted alkene. So in the kinetic product, the bromine minus ion attacks the most stable carbocation intermediate, which is the tertiary carbocation intermediate. And for the thermodynamic product, our bromine ion attacks the less stable carbocation intermediate, but gives us the more stable alkene product here, which is the tri-substituted alkene. So the same thing here, we form our most stable carbocation, which can do resonance throughout this whole system. We do resonance here, which also gives us this secondary carbocation intermediate. But in this case, this carbocation here that is both secondary and benzylic can do resonance with the benzene ring and the alkene adjacent to it, whereas this carbocation here can only do resonance to this alkene, which is why this carbocation here is more stable, giving us the kinetic product when the chlorine minus ion attacks that carbocation. But this double bond here is the most stable because we have a benzene R group supporting it, as well as this other R group supporting as well. So both of these alkenes here are di-substituted, but this benzene R group here stabilizes this alkene better than the R groups of this alkene over here. So let's move on to the next one. We see here we have Cl2. We react it with this double bond instead of this double bond because this alkene here is 1, 2, 3 tri-substituted, which gives this alkene more negative charges and it activates it even better, making it more nucleophilic, whereas this alkene here is di-substituted, making it less nucleophilic. So since this is more nucleophilic, it will attack the chlorine and kick out the other chlorine. As this chlorine gains electrons, it becomes more nucleophilic, and this alkene here loses electrons, making it more electrophilic, so the chlorine will come back and attack the other side of the alkene, giving us this chloronium ion. So this chloronium ion here is a good leaving group, and we want to form the most stable carbocation when it leaves. So we could have a secondary carbocation here or a tertiary carbocation here. Since we want the more stable tertiary carbocation, we're going to kick up the chloronium ion on the other side, forming our tertiary carbocation here, tertiary allylic carbocation here. So then, since this is our tertiary carbocation, allylic carbocation, the chlorine minus ion can attack that most stable carbocation intermediate, giving us a kinetic product. If we do resonance over here, then we form our most stable alkene product, which is the tri-substituted alkene, giving us our thermodynamic products here after the chlorine minus ion attacks the carbocation. And then for the next one, since these two double bonds are equally substituted, they're both tri-substituted, either one could have attacked the Br2 and we would have this intermediate. Now we want to form the most stable carbocation. It could be a tertiary allylic carbocation or a secondary carbocation. Since we want to form the tertiary allylic carbocation, we're going to kick up the bromonium ion on the other side. And the kinetic product comes from the most stable carbocation intermediate. When we do resonance here, we form the tetrasubstitute alkene, which is our most stable alkene product, giving us our thermodynamic products here after the bromine minus ion attacks the secondary allylic carbocation. Okay, and then for the next one, we see here we form a bromonium ion, we form our most stable carbocation. So in this case, this is not going to be our most stable carbocation. Even though this is tertiary and this is a secondary, this secondary carbocation is more stable than this tertiary carbocation because this secondary carbocation can do resonance with the double bond adjacent to it. So since this carbocation is allylic, it could move around these 3 carbons here. And if it's delocalized, then it's more stable than this localized tertiary carbocation here. This tertiary carbocation cannot do resonance, which makes it less stable than the secondary carbocation that can do resonance. So this is why this is the kinetic product here. And the reason why the bromine minus ion attacks the tertiary allylic carbocation instead of the secondary allylic carbocation, because this tertiary allylic carbocation is more stable than the secondary allylic carbocation. And this is our thermodynamic product here, where the alkene here is tri-substituted, whereas this alkene of the kinetic product is di-substituted. Okay, let's move on to the next question, which is the mechanism and which is the thermodynamic product. We see here we want to form the most stable carbocation, which is going to be this tertiary allylic carbocation here. When we do resonance, we form the primary allylic carbocation. And that's for part A, when the bromide ion attacks the primary allylic carbocation, giving us our tetra-substituted alkene. For part B, we form the tertiary allylic carbocation here. And when we do resonance, we form the secondary carbocation. And this also gives us a tetra-substituted alkene. So since the alkene is equally substituted, which are both tetra-substituted, we look at the conjugate pair and which one is more stable to determine our thermodynamic product. Since the conjugate pair of A is tertiary and primary, whereas the conjugate pair of B is tertiary and secondary, the conjugate pair of compound B is more stable than conjugate A, which makes this B compound the thermodynamic product. Now let's move on to the next part. We see here we have CO2. When we reacted with this alkene over here, we're going to form this chloronium ion. We want to form the secondary allylic carbocation. And once we form that, we could do resonance with that. And both these resonance forms have secondary allylic carbocations, and they're both disubstituted. So since they're both equally stable in terms of the carbocation intermediate and double bond, then they're both the thermodynamic product and also the kinetic product as well. Now let's move on to the synthesis problem. We see here that in the reactant and the product, the only difference is this new R group that is added to the anti-Markovnikov position of the double bond, or the less substituted side of the double bond. So for the synthesis problem here, we could make this anti-Markovnikov position electrophilic or nucleophilic, and then add the new R group that way. So let's first look at the synthesis where we make that less substituted carbon electrophilic. So the first step would be to do hydrogen oxidation, which is going to give us the anti-Markovnikov position of the alcohol. And then once we have a primary alcohol, we could oxidize that into an aldehyde using PCC. And now we formed an electrophilic carbon here, where we could use a nucleophilic R group, like a Grignard reagent, to attack that electrophile, and then kick open that carbonyl onto that oxygen. And then I started the attacking carbon and dotted the carbon being attacked to form the new bond between them to keep track of what groups are attached to which. The MgBr will dissolve away in the solution. And then we do acid workup to protonate the O- ion, giving our alcohol here. And then we want to convert this alcohol into a good leaving group like Cl or Br. If I use SOCO2, I will convert this to chlorine. If I use PBr3, I will convert that to a bromine. In this case, I used SOCO2, which converts that into a good leaving group, chlorine there. And then I could do an E2 reaction here by introducing a strong base like ethoxide here, and grabbing the hydrogen, forming the double bond there, and kicking out the good leaving group, giving us the final product that we want. And this is the synthesis for when we make the anti-Markovnikov composition electrophilic. Now let's go on to the synthesis where we make the anti-Markovnikov a nucleophile. So the first step here is to do Br2CCl4. What I'm going to do here is I'm going to make this an alkyne anion where we have a terminal alkyne and turn that into a nucleophilic group. So the first step to convert this alkene to this terminal alkyne is to do Br2CCl4 to add a vicinal dihalide here. And once we do the vicinal dihalide, we would do 3 equivalents of a strong base. And also there would be an acid workup step as well. This step 2 and 3 would also be included in here as well. Will give us our terminal alkyne here. And once we have a terminal alkyne, we use a strong base like LDA or NaH2 to deprotonate this terminal alkyne, giving us our nucleophilic compound here. And then we introduce an electrophilic aldehyde here. Since we see that we added a 1,2 neocarbon chain, 1,2, then we're going to add 1,2 here. Star the attacking carbon, dot the carbon being attacked, make the new bond between the starred and dotted carbon, kick up the carbonyl oxygen on to there, reprotonate that alcohol, turn the alcohol into a good leaving group using SlCO2 or PBr3, do an E2 reaction, form the new double bond that we want in the product, and then convert this alkyne into a trans alkene by using sodium metal and NH3 liquid. And the shortest synthesis for this is just one step, which is the Heck reaction, where we use this this compound and palladium metal with heat, where the simplified mechanism is where palladium will insert itself between this chlorine and carbon atom, making this carbon connected to the palladium nucleophilic, which will attack the less substituted side of the alkene here. And at the same time, the more substituted side will attack the palladium. We see here, I dotted the carbon being attacked. I started the atom that is the attacker. We see the new bond between the atom that is attacker and the atom being attacked. Here, we see this more substituted alkene attack the dotted palladium. And then the very last step here is, this is a simplified mechanism. The hydrogen here will form a double bond there and kick out the palladium, kick out the Cl at the same time, giving us our final product here.